Hi, I'm Charles, and welcome to my video on my multidimensional generalization of the Collatz conjecture. In this video, I want to talk about a simple algorithm that I came up with that generalizes the Collatz conjecture to multiple dimensions, and just go through the code I used and the algorithm, that sort of thing. So this is what it looks like. The three-dimensional generalization, and yeah, I'm going to explain what all the points are and what they mean. So I think to get started, we can look at the actual Collatz conjecture. So here is the Wikipedia article on the Collatz conjecture. This will tell you about basically what it is and, information about it, but it really boils down to you start with a number, a positive number greater than or equal to 1, and if it's an even number, so n is equivalent to 0 mod 2, you divide that number by 2, and if it's odd, if it's equivalent to 1 mod 2, you multiply it by 3 and add 1. So I have a document here that also goes through that, and I'm going to go through this briefly and just demonstrate how to increment these numbers, and also in the multidimensional case. So this is essentially what the document says. You start with some number n that's a positive integer, and if it's even, you divide by 2, and if it's odd, you multiply by 3 and add 1, and that gives you the next number, and then you do the same thing with that number. So we could do a simple example. If we start with the number 5, 5 is odd, so we multiply 5 times 3 and add 1, and that gives us 16. And 16 is even, so 16 over 2, we do 16, we divide by 2, that gives us 8. Then 8 is even, so we divide 8 by 2, that gives us 4. Then 4 is even, so we divide by 2, and we get 2. 2 is even, and so 2 over 2 is 1. We divide by 2 because 2 is even. 1 is odd, so we multiply 1 times 3 plus 1, and that gives us 4. And so we found this number 4, and we've already seen 4. So essentially what will happen is this cycle, it's called a cycle, and it will repeat over and over and over again. So it'll go 4, 2, 1, 4, and then 2, 1, 4, 2, 1, etc., etc. So this is the cycle, and every number, and I believe they've tested some really large numbers. Some scientists have tested some really large numbers, or just people have tested really large numbers, and they all come back to this cycle for the Collatz conjecture. But nobody can prove that that happens for every number. I mean, people think that it does, but we don't know. So I have made the problem worse by adding multiple dimensions to it. And in some cases it converges, and in some cases it appears that it doesn't. But I don't have a proof that these the starting values don't converge. They might not converge, but they also could. So it's hard to say. Anyway, I'm going to continue to go through the document. So the multidimensional generalization of the Collatz conjecture. We have a vector of integers of size n. So that essentially means we have a vector. So like here, this is a vector of length 5, 1, 2, 3, 4, 5, although by convention the indices start at 0. And each of these values is an integer. And so the update rule, like the normal Collatz conjecture update rule is, so we look at the values of the vector, and if every value is an even value, so it's divisible by 2, we just divide every value by 2. Fairly straightforward, and then that becomes the next vector. But if there's even one value that is not divisible by 2, that's an odd value, we multiply every value by 3, and then we add that value modulo 2. So that could be a little bit confusing, but what this essentially means is that for the values in the vector that are even, this value would be 0. So 2 modulo 2 is 0, or the remainder of 2 divided by 2 is 0. But if the value is odd, we multiply by 3, and then 3, this value would be 3, and modulo by 2 is 1. So 3 times 3 plus 3 modulo 2, which is 1, is 10. So that might be a little bit confusing, so I'm gonna go through an example down here. So we start with this this vector. This is a 3-dimensional vector, and we start with 4, 2, and 6. And so 4, 2, and 6, they're all even. So we divide by 2. So we get 4 over 2 is equal to 2, 2 over 2 is equal to 1, and 6 over 2 is equal to 3. And that goes into our next vector down here. So that's how we transform this one into this one. And so, okay, this actually demonstrates it fairly well. So we have 2, 1, 3 in this vector. We have 2 odd numbers and 1 even number. So we follow the second part of the update rule, which is this. So 2 times 3 is 6, and 2 modulo 2 is 0. So the 2 in this vector is transformed into 6. The 1 is multiplied by 3, and then 1 modulo 2 is 1. So we have 3 here, and then 1 modulo 2, we have 1. That's 4. So the 1 is transformed into a 4. And the 3, multiply 3 by 3, that's 9. And we modulo 3 by 2. So 3 is an odd number, so we get 1. And then we get 10. So now all the values are even. And so we follow the even rule. We divide everything by 2. 6 over 2 is 3, 4 over 2 is 2, and 10 over 2 is 5. And now we have odd numbers in here, so we follow the odd rule, multiply by 3 and add 1, 3 goes to 10, multiply by 3, but we don't add 1, so 2 times 3, like up here, 2 times 3 is 6, and for 5 we go 3 times 5 plus 1, which is 16. And so then we follow the even rule, then the odd rule, etc., until we keep going and we get to this value, and this value doesn't seem particularly important right now. We just keep going, follow the even rule, odd rule, even rule, odd, even, odd, even, odd, even, odd. This goes on for a while, and then we get to here. And here's this value again, which we've seen before. So 24, 16, 36. If we scroll up here, we get 24, 16, 36. So that means similar to when we were just looking at the normal Collatz conjecture, and we found that 4 goes to 2, goes to 1, goes to 4. This is a fairly small cycle, but for the multidimensional case, there's a few more steps involved, but essentially, if we start at 24, 16, and 36, we go all the way around through all these numbers, all these different vectors, and then we end up back at 24, 16, 36. And so now this is in a cycle, and it'll just keep going infinitely if we were to continue the update rule. So yeah. This, something to note is that this works in the negative case, so we can do this with negative numbers as well, negative numbers in the vectors, as long as they're all negative or all positive. I've noticed that if you have a mixture of positive and negative numbers, that doesn't work. But if you have them all negative or all positive, that works. And this is Python's definition of its modulo operator. So if a and b are integers, a modulo b is equal to a minus b times the floor of a over b. Fairly straightforward. This is the two-dimensional case. And as you saw before, that's the three-dimensional case. And then there's some notes. This will be on the GitHub, so feel free to look if you're interested. So here is this. All these values are they're values where the sequence ends up converging to a cycle, like in the example we did before. Everywhere where there's empty space within like these three lines, in like this positive quadrant, this strictly positive quadrant, and this strictly negative quadrant, all the empty space, so if we look like these spaces here, those are values that did not converge. So if I turn on the crosshairs, we can see that like all these values that are colored in converge to a cycle. And we can notice that everything on this main diagonal converged. It's a little bit hard to see, but they are all connected, but they should be. And also on this diagonal, and then also on these lines, because on the diagonals, you have essentially all the numbers are the same. So it's 1, 1, 1, 2, 2, 2, 3, 3, 3, and or in this case 1, 1, 0 or 2, 2, 0, and in that case it just turns back into the regular Collatz conjecture. So essentially, when you get off these main diagonals is when like interesting stuff happens, and you start to see what it almost looks random, but it still has a pattern. But yeah, so the diagonals and these lines and this main diagonal, and there would be other diagonals in higher dimensions, but they'd all essentially be the regular Collatz conjecture. And then everything everywhere else is the multidimensional Collatz conjecture, or my multidimensional generalization of the Collatz conjecture. So I did not write this code in OpenSCAD. I found it easier to write in Python. So this is the negative side. Both sides are kind of interesting, a little different. Here's the code. So essentially it takes a tuple of an arbitrary length. We calculate the modulus of 2 for every value in the tuple, and this calculates if all values are even, and if they are all even, then they get divided by 2, and if they're odd, they get multiplied by 3, and then this mask is added back to it, which is like if a value is odd or even. So that essentially, this is the update rule essentially. this is searching, this determines, this piece of code determines whether a vector converges to a cycle, like a starting vector converges to a cycle. And something important to note here is that there's a max step, because like some of them kind of just shoot off to infinity. And it's possible that those ones converge, but we don't know. Like, I don't know if they converge or not. So I have to set like a maximum number of steps to count for, or else they could just keep going indefinitely. So it essentially searches a certain number of steps, and there are much more efficient ways to implement this, and Python would not be the fastest language to implement this in. But this is just a proof of concept, an easy proof of concept to give a demo. And this essentially just calculates all the points. It just goes through the three-dimensional space. Where is it? Yeah. This piece of code just goes through the three-dimensional space and looks for convergence for each point. But you'll notice, so in this, only the strictly positive and strictly negative quadrants were considered in the three-dimensional case and in the two-dimensional case, because I found that like none of these other values converge to a cycle, so it was much more computationally efficient to just consider the strictly positive and strictly negative. So yeah, that's what this does. It, uses this piece of code, the run cycle code, to essentially look for the starting vectors that are bounded and end up in a cycle. And this just essentially writes the files out. So this is just I think boilerplate code to create the files, the OpenSCAD files for viewing. So this is the three-dimensional one. And I'll put the viewing files on GitHub if you want to download them and see for yourself, as well as the Python code. So there's that, and now I'm gonna generate the two-dimensional version. So I just need to change this, and the OpenSCAD code is not quite right here. I can actually just change this to a 1. But I'll be changing it to the three-dimensional version for the GitHub version. You can just make this, it's a simple change, and it doesn't fully break it, the OpenSCAD file, but it just makes it proper. Anyway. There we go, so it generated, so I open the viewer, and here's the two-dimensional version. And you can change like how far you want it to go. Like you could go to 35. Maybe let's go to 40 instead. Like if you just want to search a further space, like a larger space of values. And in this version, we count to like 200 steps. It's the max number of steps that the program will consider before it says, okay, this thing probably doesn't converge. So yeah. And for some reason it's, oh, okay, so it's not happy about that because these values need to be 40. There, and now we just have a bigger version to look at, and you can see that like it's yeah, it just grows. Like there are these kind of like angles that it shoots out at. But it's not just quite a straight line. It's a little bit more complicated, and then it has these weird kind of shapes that come off the main diagonal. Anyway, thank you for watching. That's the gist of the video. Yeah, thanks for watching, and hopefully I'll see you in the next one.